So we are going to embark on the final topic of decision maths, linear programming, and optimisation of things you want to optimise. So here's an example of something you might want to optimise. You are selling apples and bananas, and you make some profit when you sell them. So for every A kilograms of apples and B kilograms of bananas that you sell, you make the profit 5A plus 2B. And that's what you make, that's your profit. So we want to sort of think about how you would plot that as a line. And the thing is, it doesn't really make sense. For example, if we have A is 10, B is 10, then C is 5 lots of 10 add 2 lots of 10, which is 70. So how do we plot that? We could do that, but we can't really connect the information about A and being 10 and B being 10 and C being 70, because that's 3 pieces of information and we've only actually got 2 dimensions on our graph. Now, there is another place on the graph where the profit would be 70, which would be when we just make, no, hang on, when else could we make it 70? I know, we could make no apples and 35 bananas. So if we make no apple, or produce no apples, produce 35 kilograms of bananas, then that's going to be up here somewhere. That would produce a profit of 70 as well. Or we could produce no bananas and
70 lots. 70 over 5.
Whatever that is. 70 divided by 5.
14.
14. I knew it was something to do with 7. 14. So if we produce 14 kilograms of apples and no bananas, we will also make £70 profit. And in fact, there's infinitely many combinations of apples and bananas, all of which would produce a profit of £70 or whatever it is. So what we can do is we can draw a line. It's obviously not going to be a very straight line, apologies. We can draw a line like that, and that line represents the profit being specifically 70. Now I could equally have done that for 50 or 10 or whatever, and then I would have got another line down here or another line down here. So this might be the line corresponding to the profit, all the places, when no matter how many, all of these places along here, the combinations of apples and bananas that I'm selling make a profit of £10 or something like that. So what's happening is that the line is moving parallel to each other, and the further right that I go, the further up, the bigger the profit. But everywhere on that line, the profit remains the same, the profit's constant. So this might be C is 10, this might be C is 30, this one obviously was C is 70, and so on and so forth. So even though we can't plot this line, we can plot that line for a fixed C, for a fixed profit. So we can see all the places where the profit would be that particular thing. Does that make sense? Mm-hmm. Okay. So we're going to use that to see how we can maximise profit. So for reasons that we don't understand, known only to the apple and banana community, we can't just make any amount of apples and bananas. We have to make an amount of apples and bananas that fits into this region, which is indicated by an R. So we basically, whatever that C represents at the moment, we can't make that much profit because there's nowhere within that R combinations of apples and bananas that would make that profit. So if we move our line, so this might represent, so don't forget, every time I move this, I'm increasing C. So this is all the places where the profit is 4. This is all the places where the profit is 5. This is all the places where it's 6, etc., 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 7, 8, 9, 10. Now this I could do. I could do this. There's a little place in the feasible region here somewhere. There he is. And at that point, the profit is 12 or something. But I want to make the profit as big as possible. So profit all the way along here, profit might be 20. All of these points here, this might correspond to C as 20. But obviously I can go further right, and further and further and further and further and further and all the way up here. So all of these points, these might correspond to the profit being 50 now. I don't know, I'm making it up. And I can go further. No, don't want to move you. I can go further and further and further. And then this, what happens here is, there's only one little couple of points there where maybe the profit is 70. I can go a tiny, 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 tiny bit further onto that corner point there, and that might be profit is, I don't know what it is, but say it's 100. Now I can't go any further, because if I go further, there is nowhere, yeah, it disappears out of the region. So there isn't anywhere anymore that's in my region R that's going to give me that much profit. So because I need to stay in the region R, that's the furthest I can go. So this vertex here, this corner, represents the values of the apples and bananas that are going to give me the maximum profit. If I'd been looking at cost instead of profit, obviously I would want to minimise it. So I would be going, how low can I go? How far down? How small can I make that cost? And it would be this vertex here. This would be the minimum, because I can't go any further left without my line leaving the region altogether. So, obviously, it's always going to be a corner. That's the main thing, is it's going to be a corner, because you're trying to go as far as you possibly can. So you'll hit a corner last of all. So minimising to the left, maximising to the right. So, all we need to do really is work out how I drew this line, which we did talk about a minute ago on the last slide, and then how we're going to find the coordinates of the corners. So, coordinates of the corners, we need to know the equations of all the lines. Now I did this on a separate slide deliberately because the most common mistake students make is that they don't write these down when they plot the lines. So it's really, really important that you write down the equations of the lines. So what we were doing there was called the ruler method for finding the vertex. So we've got a ruler, and you can actually use an actual ruler and another ruler like this. And we need to move this line parallel. So if you create a right angle between your two rulers, then you can move it across and keep that right angle going and see which corner is going to be the corner that you'll get to last. And then once you do that, you can say, well, this is where this one crosses this one, and then you can do simultaneous equations. Make sense?
Yep.
Okay. There is another method, other than the ruler method, which is called the vertex method. Here it is, vertex method. Now, the vertex method is a bit more clunky. The vertex method has nothing to do with this red line, this optimization line, nothing to do with the ruler. The vertex method says, I know that the maximum will occur at a corner. I just don't know which one. So I'm going to work out the coordinates of this corner, the coordinates of this corner, the coordinates of this one, and the coordinates of all of them, and literally work out which one's best. So it seems much more clunky because
it's much more working.
Yeah, it's much more working because you literally do have to work out the coordinates of all of the four corners. There may be more than four corners, and then you have to put them all into the equation that you're trying to maximise to see what the profit would be, and then
so it's 4 sets of simultaneous equations and then 4 substitutions.
Yes. And then, oh look, that one's the biggest. When it's perfectly obvious which one's going to work anyway. So, but sometimes in the exam they say use the vertex method. If they don't, nearly everyone goes for the ruler method. Okay, so the only thing we haven't discussed is where this red line came from and how we plot the original one. If we go back a couple of slides to when we were talking about this line, well, each of these lines corresponds to a specific value of C, a fixed value of C. So all we need to do is make up a value of C. It doesn't matter which, it could be 10, it could be 30, it could be 70. And then substitute that in here, just your favourite number, whatever it is. Plot this line, which will turn out to be one of the ones that I've drawn there. And then you've got your line, and then you can move it parallel.
And that moving it changes that C value, doesn't
Yes, and you're only moving it literally in your mind, really. You're not drawing lots of them, you're drawing one and then moving a ruler like this, or your pen, to see which vertex it's going to hit last, basically. Okay, let's have a go at an exam question. Right. Shall I give you the pen and you can have a go? So, what we're trying to do is maximise, so we're going to try and go as far right as we possibly can. This is the region that we're allowed to be in here.
So we're aiming for as far that way, right?
Yeah, as far that way as possible. So we're going to start by plotting, maybe we should use red for our line since we used red before. We're going to plot our line that represents our profit.
Right.
So do you remember how we do that?
So we need to pick a value for P.
Excellent. We need to pick any random value for P that you like.
I'm trying to think of something that would be nice in our equation. P-T?
80 is going to be nice, yeah. I mean, you can literally have anything. I mean, you're right, 80 is nice, or 160 would have been nice, 240 would have been nice, 10 would have been not so nice.
No.
But you can have anything.
So that's...
So you can kind of think when x is, simplifies down. So when x is 0, what would y be?
Y would be 1.
Yep. When x is, and then when y is 0,
X is 1.
yeah. Now, how easy is it going to be to plot that on our graph? Not too easy, because we're going to go, and then try and draw a line here, and it's going to be so disappearing that we won't be able to see it. So, shall we choose a different P?
Should need to be bigger, isn't it? Let's
Mhm.
try 800.
It's a good idea.
Okay. So when x is 0, y is 10.
Yep.
And when y is 0, x is 10.
Excellent. Yep, that's right. So we can now draw a line. Actually, if we put our pen down first and pick it up again, we'll be able to move it.
Move.
The line.
This one.
No, the line you're about to draw. Yeah, that's it. Beautiful. And it's fine to extend it as well. You can sort of, because it represents the whole thing. So along this line, the profit is £800 or whatever, and we label it profit line. Like that.
This is our optimal.
Yes.
Optimization line.
So all the way along there, the profit's 800, but the trouble is, nothing along there is in the region R,
No.
so it's no good to us anyway.
we need to
So we need to move it parallel to itself. We should be able to actually, we can move this little bit. So we can move that. So you have to try and move it parallel to itself without changing its angle at all, and see how far right you can go before, it's fine that that's there, before it leaves the feasible region. So which corner is the last one? That's the first one, it's hit. That would be the lowest profit possible.
So
in
it'd
this
be, if
feasible
we were
region.
costing, that probably would be the
Yes,
second
we'd
one,
want
yeah.
that corner there, yeah. Now this is going to be really difficult to see which of those.
Well, let's imagine it's a little further along. I think it's going to hit that top corner next. Do you agree?
I do agree, yeah. Should we make it longer? Let's, oh dear. Wait, control Z.
Beauties of technology.
Right, do you want to, if you get the green pen and draw all the way down that. That's it. And then if you put the green pen now, we should be able to move that green one.
There we go, yep, got it.
Yeah. There we go.
There we go. Right, so we said we hit that one first.
Yeah, so if it was cost, that would be the corner we'd want. And that's it.
Hold on a minute, look.
Yeah, there you go, you're right. It's hitting that top one next.
So if we're maximising our...
We want to keep going to the right as far as possible. Keep going with that line. And that one.
We'll hit it.
We will move. Yeah, I see what you mean. It is more difficult than it looks. There it is.
Perfect.
That one. So at this point here, we're completely out of the region. It's no good. None of those points are any good at all. That there, that's the vertex that we want.
Yeah.
Okay. So, what are the coordinates? Well, luckily I have labelled lines. So it's this line and this line.
Yeah.
So we're going to do simultaneous equations. Do you want to use the space on the right? So we're going to use simultaneous equations to get the coordinates.
So first equation, second equation. know what x is.
Yeah.
So 5 lots of 5y. 6y.
Yeah.
Which is 31. Lots
Yeah.
of y.
Calculator.
5 is 30.
Calculator. Okay, so that is, what is it? 300 divided by 31, 9.67. I suppose the exact is nicer, but anyway.
Yeah.
And then the x will be 5 times that, which is 48.39. Yeah, and again, I think exact is nicer, but
Particularly when you're still going to use this to manipulate later.
yes, exactly, yeah, because we're going to use that to work out our actual
So that
profit.
would be 1500.
Yes. So, in order to get the maximum profit, we need x to be 1500 over 31, and we need y to be 300 over 31, in which case our actual profit, because obviously that's what we're interested in,
Yeah.
is 80x add 80y. So then we'd put that in and we'd get our actual profit. So it is 80 times 300 over 31 plus...
Oh, you want x though. Oh, you
Oh, I
want-
put in, yeah.
yeah.
No, you're right, x isn't that. That was y. It's 1500. 1500 divided by 31.
Yeah.
And then add on 80 lots of y. Oh, actually, they're
Didn't
both
matter,
80, so
yeah.
it didn't matter, did it? Being stupid. And that comes to £4,645 profit. So all the way along this green line, every combination
Yeah.
all the way along here of x's and y's causes the same amount of profit, but the only one of all those crosses that's in the region that we're allowed to be in
Yeah.
is that one. So that's the solution to this optimization problem. Now, that obviously we could have done the vertex method, which would have meant that we would do simultaneous equations on this, 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 all those. Then we'd got 1, 2, 3, 4, 5 combinations of x's and y's. We would calculate the profit for all 5 and then go, oh, that one's the biggest. And then we'd know that was the biggest. So the solution to the problem is, if we go back to the original problem, is that we should buy apparently 48.39 cars.
Fine.
Fine, apart from that you can't buy 0.39 of a car.
Which third do you want?
Well, exactly. So this is fine and everything. We've done really well, but because you can't buy 9.67 cars and you can't buy 48.39 cars, you've got a bit of a problem.
Yep.
So what we need to do is go back to our green line and say what is the last integer point that we hit, not the last corner.
Because it might not be what you want to just round, is it?
Yeah, exactly.
So-
We do need to stay in the region. So what I've got here is a zoomed in version of the region. If we put our line back on, here it is, drawn on nicely for us, like that. If we move this to the right, like that, that was us hitting that
Yeah.
vertex last of all. But we need an integer point now. So what's a good tip is to get a ruler and have a look where the integer lines are. So this line here
That would be 10.
is y is 10, yeah. Now, y is 9 is here. Like that.
Yeah.
Now, x is 450. Each 2 dots is 1, isn't it? So this,
No,
isn't it?
that was one.
Each dot is 1. Good point, each dot is 1. So this here is x being
48.
48, and this is x being 47. And I don't think, I could go up to one more y, but I don't think I'm going to get any more inside
No.
the region. So I think the crossing, the integer points, the ones where they're whole, that are inside this region are going to be, well, that one definitely is. That one definitely isn't.
Yeah, neither is that one.
That one definitely isn't. This one looks like it might be, and this one looks like it might be, although I might have to check those, to be honest.
Yeah.
I'm not 100% sure. So if I get my green line now, and I see which of these am I going to hit last? Well, it's not that one.
No.
unless the other two aren't in it.
Yeah.
Oh, it's so close. I think I'm hitting, in the same way that we hit that top corner first, I'm hitting that top one first.
Yeah.
And so it's that bottom one there.
Which is 10.
Which is, so it's this one here. And this was the y's that were 10.
Yep.
And this was the x's that were 48. So, provided that is in the region, which we could check just by using the inequalities that you'll see in the next video, we can just check that that is in there. And if that is in there, then the actual maximum profit is 48 and 10. So if we go back and compare that to what we got a minute ago, well, we said 48.39, we're now going down to 48.
Yeah.
And the 9.67 is going up to 10. So you can see it's nowhere near as simple as just rounding them both up, or they might both go up, they might both go down, one might go up, one might go down.
I mean, in this case, we were lucky that actually our intuitions to round it would have been right for them.
Yes,
I mean,
that's true, actually.
How close they were in the last slide.
That is true, because that would round down and that would round up, but you can see that it is nothing to do really with rounding. It's to do with you really focusing in on that point, on that vertex, and looking about what's going on.
So in an exam, if I can't see that vertex that clearly, what's my best bet?
It's a good question. I think you kind of have to be able to. I suppose the other thing you could do is that you could just concentrate on all of the integer points around there. So we know x is going to be 47, 48 or 49.
Yeah.
Really. I mean, it's going to be one of those three.
Yeah.
And I can't count. And we know y is going to be 9 or 10 or 11.
Yeah.
So it gives us a few things to play around with. We could put each of those in and test whether or not they're in the region. We'll play with that in the next video. So we could test if they're in the region, and then once we know which of those 9 integer points are in the region, we could put them all into the profit and see which one is going to give us the biggest profit. But the important thing is that we stay in that region, that we don't deviate from that region. Brilliant. Okay. So in summary, we've got two methods. The vertex method, which is where you calculate the coordinates of all of the vertices of the region and then put them all into the function and see which one's biggest or smallest. And we've got the ruler method, which is where we plot the line representing the thing we want to maximise or minimise by choosing a random but useful number.
For instance, our 80 wasn't
our 80
useful,
was not useful, but then 800 worked much better, yeah. Plot it, label it, and then use a ruler to move it parallel, work out which one you're going for, which vertex, and then you only need to do simultaneous equations on that one to find the coordinates, and then simply sub that back in, and that's your profit. And just be careful if you do need integer values. So if you're buying chairs or cars, you can't buy 0.67 of a car, whereas if it's just an abstract problem, then it's fine to have x's 2.72. Brilliant. Well done.